So in this video we're going to show an example of using trigonometry to convert from parametric into rectangular form. And this is going to be a pretty common technique that shows up. So here we have parametric equations: x equals 3 cosine t, y equals 5 sine of t. And t is running over the interval from 0 to 2 pi, so one full trip around a circle. So the idea is to take advantage of the Pythagorean identity. So the way that we can do this, y equals 5 sine of t. It's a horrible 5 that looks like an S. The way that we can do this is we isolate the cosine and the sine function. So over here I would divide both sides by 3. My brain just got ahead of myself. And over here I would divide both sides by 5. And then what we would do next is square both sides. So if we do that, we get x squared over 3 squared equals cosine squared of t. And over here we'd have y squared over 5 squared equals the sine squared of t. And then what we do is add the two equations together. So I add the left-hand side of each of the two equations together. So I do x squared over 3 squared plus y squared over 5 squared equals, and then I'm going to add the trigonometric sides together. So if I add these two sides together and they're equal, then it should be equal to adding these two sides together. So over here I get cosine squared of t plus sine squared of t. And then here I want to recognize the Pythagorean identity. Cosine squared plus sine squared equals 1. So I have x squared over 3 squared plus y squared over 5 squared in rectangular form. And then what I want to recognize from this is that I really have the equation of an ellipse, which is why it's important to review conic sections and the formulas for parabola, ellipse, hyperbola, circle, because those are going to show up increasingly now as we move forward. So if I recognize this as an ellipse, I know I can graph it in the xy plane fairly easily. The smaller number squared is under the x, so that means the x is corresponding to the semi-minor axis. The larger number is under the y, so y is this 5 corresponds to the semi-major axis. So that tells me that my ellipse, which hasn't been translated from the origin, is going to be taller than it is wide. So I'm going to just sketch in something that's taller than it is wide as best as I can. A taller than it is wide ellipse. And then once I sketch it, my horrible sketch, I want to recognize that in the x direction, the semi-minor axis is 3 units, so I need a total of 6 units. So it's going to run from -3 all the way over to 3. This number gives the length of the semi-minor axis, the distance from the center of the ellipse to the far edge. And then this is running based on the 5 here. It's going to be running from 5 up there to -5 down here. And the only thing that we have left to deal with, other than the fact that my ellipse is very poorly drawn, I probably should have pre-drawn it in GeoGebra to give you a nice clean picture. So here's my x and my y axis. So these are trigonometric functions, so we want to recognize that as we run from 0 to 2 pi, we should be rotating counterclockwise around this. We could verify this just by plugging in a couple values for t. So for example, if I plug in t equal to 0, cosine of 0 is 1, and so when t equals 0, we get the ordered pair 3, comma, sine of 0 is 0, 0 times 5 is 0, so we start in the 3, 0 position. And then I could just say, what happens when I put in the angle pi over 2? Where do I wind up on the ellipse? So if I plug in pi over 2, so if t is pi over 2, I get cosine of pi over 2 is 0. 0 times 3 is 0. Sine of pi over 2 is 1. 1 times 5 is 5. So I'm running up here. So that kind of verifies it as I move from left to right on the, if I'm thinking about it as a t-axis, as I move in the positive directions of t, I am moving in that counterclockwise direction that I expect from my background in trigonometry.